So welcome to session 3A. So if you're interested in water interest in the growing semiconductor industry, you're in the right session. If you are looking for session number, what's the other one? 3B, preparing the next generation professional pathways in water, you need to be in the other room next door. But this is the better session. This is the right session. My name is Stefan Grimberg. I'm going to be the session moderator for this session. So welcome to the session. We have two excellent speakers and myself presenting here, talking about various aspects of treating waste from the semiconductor industry. And so the first speaker I want to introduce is Moha Bhatia. He is now with AECOM. He used to be with EPA for quite a long time, I believe, right? He used to be a group leader at EPA, looking at various aspects in trace contaminants and mitigating environmental risk from various waste streams. And he has a lot of experience in this kind of waste material. And so we're delighted to have him talk about this topic today. His specific bio is in the audience, is in the program, so I'm not reading everything that is in there. So thank you for being here.
Thank you. Okay, wastewater. Again, if you're in the wrong session, this is your home session again. No one is leaving. Oh, we're getting more people. That's good. Okay, so as Stephen mentioned, we have two follow-up talks. My goal today is actually to set the stage for them. I'll get the zoom out. I like that exercise. Tell you about what are the challenges, what are the opportunities, and then Stephen will talk about azoles and treatment, and Alan will also follow up with some treatment work as well. So let's start. Why are we having the conversation about that today? I think it's no secret that fabs are growing in size, but also the numbers of fabs that are being built is increasing. Do you know from like a lot of chemicals, a lot of solvents are being introduced during the production of semiconductors? What is the largest by volume solvent used in the production of semiconductors? Sorry? Let's hear. Water. Okay. What kind of water?
Super pure.
Yeah, I like it super. It's called ultra pure, so it's not just clean, it's not just pure. It has to get to that ultra pure water. So like from a solvent, it's not like your regular water anymore. So the water pressure is very big there. So it's not a wastewater only, it's also the water that gets into the process itself. But then layer by layer, I don't promise that I'm going to oversimplify, but trying to communicate the complexity of the challenge that we are facing. So the water that gets in and other solvents and many other chemicals, they have very specific function. That's a very expensive production line. Nothing is being used there basically because it's cheap or they are having fun. Everything there is there for a specific function and it's not cheap. And that means that soup of chemicals or different families that we are seeing on the screen are there to deliver that function. But then that's when the wastewater complexity comes to play. But what after, and then like, let's discuss what happened beyond the fabs. So like permitting, wastewater discharge, regulations, maybe. So that's why I think when people think about semiconductors, it's the exact same word used for many decades. But 4 decades ago, it was a big device. Now we are talking about nanometer. So it's not only the size of the device that got smaller. To get that small, the fabrication also went through multiple kind of advancements. So if we talk about like 80s all the way to the present day, what you have there and what I'm trying to communicate with you are three things. What is the technology that has been used? What are the chemicals that have been used in that period? But what about the reaction from a regulation point of view? Any alignment, any lag or gap? So pay attention, okay? So again, 4 decades ago, we were talking about the semiconductors at that time, a breakthrough, but it was big. And what you see there is chemicals are being used, mainly hydrofluoric acid and some other acids, base, etc. Couple decades, I wouldn't give you more information about like the exact description of technology, but again, you need to pay attention that the chemistries that are being introduced to that process is changing. But what you see down there is that actually the discussion in 1998 was about the chemistry of the 1983 chemistry. After that, again, when we went all the way to the nano scale, more chemistries are being introduced, including PFAS. But you can see that down there, there is quite a gap. Until 2022, this is not regulation, just like a list of chemicals that we should be concerned about. Why we're, again, discussing that today, because we see that there are more push towards regulations of PFAS and other emerging contaminants when it comes to the discharge from semiconductors fabs. So it's the exact same word, semiconductors, but it means different thing throughout that period of 4 decades. So one would say, like, do they know anything about that? To be fair, like again, zoom out or be fair, these are two keywords I like. So the semiconductor industry, actually, they have that SIA, Semiconductor Industry Association, 3 decades plus. They have been studying what's getting in, what's leaving the facility. It's just like very tight circle, but they know a lot. And that's, I guess, if you want to take home message, that there is a lot of information, a lot of funding that even comes from them that funded a lot of research question. Like if you talk to them, first PFAS membrane study was funded by that association. Some analytical work that I'll discuss later was also funded by them. Not all, but that's basically some of the disconnect that people think that they're focusing on one area, but there are others and not there. So there are white papers, there are videos, I guess, that can be found in their website in there. Okay, so laying the ground, meaning that I wouldn't talk about silos anymore. We need to connect what happened in the fab to what is happening between the fab and environment, meaning like treatment technologies, but also considering once residuals, emissions, wastewater that leaves there, how can we think about it from a holistic point of view? So they are all interconnected, they're all impacting each other, and that's how we should be thinking about it, basically. So that's basically that. Not just the mass transfer, but the risk transfer is moving from inside the fab technologies, and then later on can be distributed differently. So when I mentioned, yeah, thank you for highlighting that water is the largest solvent. To get to ultra pure water, and this is an indirect way to tell you that they know about treatment, like to get the water to the ultra pure stage. This means like you know how to treat water. But I will need now your attention because I'll have a quiz after this line. Because it doesn't just go with pre-treatment, a lot of removal of salt, desalination, biological, chemical, physical. So it is not just your regular treatment train. I gave you a warning. So, how many steps? That's the initial train. Okay, it's 15. So to get ultra pure water, you need to pass your regular source water into 15 steps. Sometimes they take drinking water, but okay. So if we get into the fab, this is just like an illustration. This fab is mega scale. But what you need to know that the processing, the steps, more than 1,500 different steps, and you use hundreds of chemicals. So you remember the mass transfer, risk transfer? I guess it goes that way as well. But inside the fab, your ultra pure water, you'll get some residuals. But also, when it moves from one step to another, they can be in parallel. You will get, again, different pathways where the contaminants will result from different steps, but also lead to different soup of chemicals, I guess the easiest way to think about it. Water conservation is one part, but also the sector is about minimizing how much water that can be used. So like the water reuse is a common practice. So knowing what is getting into that reuse step is very important. And here's another reminder. We talk about water a lot, but this is another reminder that it's not just water. Like the air, for example, from the etching process, this is just like a random example, is what is leading for some fluorinated material in the water space. So your air problem is a water problem as well. Your treatment for water is resulting in residual like solid waste. So everything needs to be put together. It's not just air, it's not just water, it's not just solid. Everything is interconnected. The relative contribution will vary, but the big picture will remain. Okay. So normally my talks are dominated by PFAS, and that's a regular one for me. But what I'm trying to communicate here is, again, not to overwhelm you that it is overcomplicated, but acknowledgement of that complication or the challenges is very important first step if we want to make it a better scenario. So high fluoride concentration is not there out of nothing. Again, processing that they use fluoride, you will get that as a result. What you're risking, you get like corrosion risk, some permitting that you will be challenged, and that's why the treatment of that is important. Management in there is just need to segregate the different waste streams and talk about that more in a bit, precipitation, etc. But you need to remember, this is not there alone. You have other developers and tetramethyl ammonium hydroxide. This is just one of the major contaminants in there as well. So you get there the risk of toxicity, and if you're using biological treatment, that will be disturbed. But it's not just one thing. So from an analytical point of view, you will need to know how to measure that in that mixture. Okay, solvents. So we talk about water, but other solvents are actual organic solvents that are being used for this different steps. So you'll get high COD value, VOCs are there, and you can see like that soup is getting more and more complicated now. Metals are there from like metal plating, the packaging steps, etc. So you'll get a variety, it depends on the technology that you're relying on. CMP process and the chemistry in there and the packaging, including azoles. And these, I guess, will be the main focus for the next two presentations. But what I'm telling you, it doesn't come alone. Again, my favorite, not really, but PFAS is there as well. So they come from different steps. And soon I'll show you that they are not going away. Okay. So, I promise, don't want you to read anything there, but that's what you are potentially looking at when it comes to dissecting that wastewater. You will get a soup of chemicals that come from different sources, different flavors. Don't taste it. But that's the mixture that you will end up having. And that translates another thing. Okay, now you're ready, right? So talking about wastewater. So the wastewater leaving there, especially if you talk about MLD or ZLD, like zero liquid discharge or minimal liquid discharge, your wastewater needs to pass through many steps: physical, chemical, biological, so that if you are considering or relying on that use as a practice to minimize your water intake and consumption. Okay. Oh, wow. Love that. Okay. Thank you. Okay. See, it's the benefit of not getting the session after the lunch. So I guess logically speaking, if we want to minimize the complexity, you need to think about segregating these waste streams. But that's a luxury because some of these fabs already built, some of them already designed. It's a very expensive process. So, and there is no clear or hard regulation pressure for some of these chemicals. But if we want to make it from a constructive point of view, how can we minimize that complexity and maximize actually the potential treatment efficiency is waste segregation. But again, from a sector perspective, someone sitting in from Micron is just like, of course we know that. We segregate different waste streams because we want to recover metals. We want to reuse certain waste streams. So it is happening, but is it part of the common practice or at the scale that we need and the source of wastewater that we hope for? Well, not there yet. But again, you remember my favorite words? Fair. So to be fair, there are actually some analytical and treatment technologies that are not really catching up with that purpose of waste segregation and management of different waste streams. What I mean by that, now I can come back to my favorite, PFAS. Okay, so why PFAS? It's not just buzzword. It is literally not going away. It's an essential part of that process. When a Cornell study published the estimation for what is the potential use for PFAS in the next 10 years, it will just keep going up. So it is there, and it is not going away. But where it is coming from, again, it's coming, like not all processes in the fab are producing PFAS or a source of PFAS. They come from certain specific units that deliver specific functions. So we have a variety of different PFAS structures, but it's now that's not as easy or metrics to characterize. So actually characterizing the wastewater in there is one of the major challenges. So if you want to convince someone that you need to do better, you need to show them how. And the analytical challenges are not catching up. There is can spend a whole presentation on analytical work for semiconductors, but NMR, for example, is catching up because it can avoid a lot of limitations. You remember first column, it was fluoride. If you are trying to quantify, I guess the previous presentation on the PFAS destruction, if you aim at mineralization to get fluoride as a final product, if you have ppm of fluoride in the background, how can you, in a reliable, practical way, quantify that or make sure that your treatment or destruction is working. It's still a challenge and a bottleneck. So this is where we are. We have, we know how to identify sources, how can we segregate them potentially, but then we can get into a reality check. What are the tools available for us that we can use to measure PFAS in air, PFAS in water? You can see now it's getting smaller menu. So there are a lot of challenges before we can put it in a comfortable way that we know how to do it. Same applies to destruction. I wouldn't go much in that. But these were kind of ranked specifically for the semiconductors wastewater. So like, it's not the same as you target other waste streams. But you need to pay attention TRL there, the technology readiness level. Things are not mature enough that if someone is, I challenge people sometimes, just like, let's think about the best case scenario. Someone comes to you and say like, here is all the money that you need. Can you solve it today? I'll put a big question mark about that. We can get a better situation, but total resolving of the issue, it still needs some more. But we need to put some more. I guess Silvana put that very good quote, like, what was it? Vision without funding is hallucination. Yeah, so that's it. Okay, so I'll wrap it up soon, but from a thought process, from a logical perspective, we know how can we make it better. This is just one of the examples. If we can segregate, pre-treat, and then think about how can we manage that waste, we can get it done. So leave you with 6 questions as of 2026. When you are trying to think about a fab better practice. So we need to think about which contaminants family control the risk. So we need to have some risk assessment. And then from that overwhelming number of chemicals, we need to think about how can we think about these families of chemicals, their sources, etc. Segregation with the hope for treatment. Then we need to think about like which streams like never be mixed, because once they are diluted, it's much more expensive to manage. But then a lower tier is just like what is worth protecting in terms of these streams. How can we evaluate that is a key to the success of the other questions. So measurements, analytical techniques, and how frequent we can do that. Like, do you really need to have an inline sensor to have a continuous monitoring for certain contaminants, or can something be more episodic or so? So that's TBD. The residuals, because again, what happened in the fab eventually will impact the environment in one way or another. Solid residuals, air emissions, and others, these need to be considered very seriously. And again, from a fairness point of view, there are certain infrastructure that are very hard to change and almost impossible to do. But if we are now in a period of time that a lot of funding is getting into designing more fab, building more fabs. So what are the questions that we should set as priorities before we have any design freeze or permitting? So that linear kind of interconnected relationship between inside the fab, treatment, and release, now you can see it's actually more, they're interconnected more than just connected in a linear fashion. Okay, I'll stop here. Thank you.
So the way we thought we would do this, we have the main questions at the end of the 3 talks, but if there's a clarifying question coming up now, we have maybe 1 or 2, otherwise we go for the presentations all the time.
No?
No. Mark?
Okay.
Go on. Okay. All right. So thank you for the start. So I'm going to dive now specifically into one particular aspect of the wastewater treatment aspect for treating semiconductor waste. So this is a study we've done for a couple of years. I'm co-authoring one of my former students and technicians, but there were lots of people involved, and I realized I forgot some of them. So already some graduate student, undergraduate students I need to acknowledge. I need to acknowledge the funding company. So I got permission to mention the funding company, which is great. Global Foundries funded that project, and the municipality, anybody can guess, is probably close by to Global Foundries. So in this case, so this is a study we've done at working on trying to figure out the downstream impact of the wastewater that comes from the fab to the municipality. And specifically, so that municipality is on a consent order to ensure that nitrification occurs year-round. And so they're obviously concerned about particular waste components which could be in the waste stream to ultimately impact the nitrification process. So for those of you who don't know necessarily what nitrification is, it's a biological process ultimately converting ammonia nitrogen into nitrate. So this is the first, as a biological process, aerobically biological process. And so we do this in typical wastewater treatment plants and a lot of those. And there's a couple of techniques we can assess essentially this nitrification inhibition of certain chemicals. One is what's called a washout test, and I'm going to talk about what that means. And another one is a batch method to test the toxicity of particular components to that. So both are pretty much standard in the industry. The one with the washout test takes 4 days or 5 days to complete. The other one is 4 hours. So there is a clear incentive on one or the other from an analytical perspective, but there's always some benefits. So talking about both of those processes, so just the washout test is a chemostat or a biological process material where you take the sludge culture from the wastewater treatment plant you're concerned about. So you take activated sludge from that plant and you feed essentially your wastewater at a higher rate than the organisms can grow. The nitrifying organism can grow. And so what that means essentially, because you don't have a clarifier sitting on the end of it, is that you're losing eventually your biomass. You're washing them out at this high rate of hydronic fluoride because they can't grow quickly enough to recuperate. And so that's what's called washout in a biological process. And so, but that data, so in other words, when you're losing your biomass, you're essentially losing your capacity to convert ammonia into nitrate or nitrate, right? And so your nitrite or nitrate concentration is going to go initially as high in the effluent, and then it goes down to nothing, right? Because you're losing your biomass, right? And so you're trying to, and this is the equation, you ultimately use your nitrate data in the effluent as a function of your flow rate. So there's flow, volume, and time. And you ultimately fit that data to determine the growth rate of the organisms and your initial nitrifying organism biomass, right? So that's really the two fitting parameters. And so the experiment, what it looks like is then something, a good example is this, where you have the nitrate concentration or nitrite concentration plotted on the x-axis over time. The blue ones are the nitrite concentration. This is nitrate concentration. And then this is the red curve is the fitted curve of that equation, what I showed you earlier. And so what you're getting is a growth rate and then an initial biomass concentration. So the process engineer loves this because they can design their reactor because they have this number and they have this number. They can design the reactors based on this number. Okay, so this is a great example of a complex waste stream. I don't know what is in that waste stream. I just know what it does to my activated sludge culture, right? So the next question is, what is a potential problem? Well, I guess it takes 4 days. That's a challenge. You have to do it with a culture, which is essentially you're trying to investigate. So in our case, it meant that we got activated sludge cultures delivered from the Albany area to Potsdam every couple of days. So somebody had to drive and get the sludge and the sludge culture to do that, to make this relevant to this particular wastewater treatment plant. So logistically, maybe a little difficult, but certainly a benefit. One question what potential could arise is the following. So these are all supposedly good fits to the experimental data at different biomass concentrations, initial biomass concentrations. So there's a variance of saying, well, do I start out with 2%, 3%, or 4% of my initial biomass concentration being nitrifying organisms? They're all best fits for those for data, supposedly. And so there is some uncertainty because it obviously impacts the engineer whether he designs his wastewater treatment plant to this growth rate or this growth rate, right? There's a factor of 50% uncertainty. So it's not absolutely perfect, but it's certainly something to consider. So you have to do this for multiple runs to really understand what is your initial biomass concentration, nitrifying organisms, to get really good, reliable numbers, data in this case. The alternative experiment, or a different type of an experiment, is nitrifying inhibition experiment. It's a batch experiment. So that's ISO, I always forget the number, it's written right there, 9509. So it's a batch experiment where we're trying to look at the inhibition. So we calculate the inhibition of a compound at a certain concentration to a control. And so I have a controlled experiment where I don't have any chemical of that concern in the solution to an activated sludge culture. And then I have an experiment where I measure nitrifying activity relative to different concentrations. And ultimately, I'm calculating that inhibition coefficient, this Ki. And I can do this I measure the inhibition, the nitrifying activity after just 4 hours. So it's a batch experiment, 4 hours, well-aerated culture. And I do this at multiple concentrations, so 6 different concentrations. And so the way this, I'll give you an example how that looked for us. So we have, for example, our activated sludge culture is constant. So we have the same amount in every of the different vials. We have different amounts of synthetic media in there. So this is ammonia concentrations are in there. We have our test substance, whatever that might be. So it might be a pure chemical, or it might be a specific waste stream, which we're trying to investigate, different amounts of that relative to the sludge culture. So everything is running at the total amount of 250 mils. And then that translates into an apparent concentration. So that 100 over 250 is 40%, right? Relative concentration, because I don't necessarily know what the concentration of my compounds are in that waste stream. We do this in triplicates. So this is for one waste stream. So you see lots of different bottles. We run them for 4 hours. And then at the end of 4 hours, we measure how much ammonia we have in each of these vials. And then we have an abiotic control and a control with 0 component as well as a positive control. And so we do this multiple times. So I give you an example for some data for some known inhibitors, azoles. So azoles are used a lot in the semiconductor industry. So we know inhibition parameters pretty much for different types of azoles, triazoles, benzotriazoles, and MEBTA azoles, triazoles. And so these are inhibition curves. So as you increase the concentration of that particular chemical, we see more and more inhibition. And what we're interested in essentially is the inhibition factor, where the concentration where we see 50% inhibition occur. So for triazole, it's 3.5 milligrams per liter. For benzotriazoles, it's about 2 milligrams per liter, and the MTBA are 2 milligrams per liter. So these are known inhibitors. So there's lots of in the literature. So our work is consistent with those parameters. Is pretty much the same. Right. So this is a very easy test to look at that particular waste stream. And so we did these because we knew these are azoles essentially used in the fab, just to essentially evaluate our tests and be consistent with some other people in that literature. want to give you an example of where we tried. So the company we worked with, we're interested in ultimately reducing that toxicity impact to the municipality. And one place where that could occur is really using corrosion inhibitors in their cooling towers. So they use corrosion inhibitors in their cooling towers like anybody else does. And a lot of those corrosion inhibitors contain azoles. Right? So these are one parts what is part of those. And the company they worked with, so the subcontractor, came up with a new formulation of a corrosion inhibitor. They tested it in terms of the efficiency of whether it actually would conserve corrosion, prevent corrosion in their piping system. And then also we were charged to look at whether that would positively impact essentially the toxicity. In other words, reduce toxicity. And so what we did is we looked at, so they have different types of products. So this is actually Nalco is the company. So they have different azole type corrosion inhibitors. And then they also have this market product 3DT398. So I don't necessarily know what's in there. It's just supposedly a chemical which has no azoles containing material. And so they did the internal testing for acute toxicity for different types of, against different types of environmental concerns, algae, fish, and invertebrates. And you can see the numbers are higher, or it's non-toxic, essentially relative to the azole-containing corrosion inhibitors. And so we tested then, so what we then did is we ultimately similarly tested that product, that 3D, that product against the one that they had earlier. So the material they had used earlier is the 3D230, which contained azoles. So there's our toxicity test of that material. So you can see at this material at about 123 milligrams per liter, you see 50% toxicity. So it's actually pretty high concentration. They think that's not very toxic, relatively speaking. When you look at the data which we received for that new component, the data is all over the place. But one thing what is noticeable is really it never reaches 50% of toxicity. It really hovers around 40% toxicity down there. Right? So we really couldn't fit a very good fit in terms of what the IC50 is for that material, for that pure compound. Remember, we're not using anywhere close to these concentrations as a corrosion inhibitor in that cooling water. So what we did then measure is ultimately we measured the blowdown. So the blowdown is every once in a while that water, which is ultimately accumulating in the cooling tower, will get released and put into the sewer system, right? So that essentially they empty out that blowdown and ultimately release that into the sewer system. And so that blowdown, we can measure the overall toxicity. And the overall toxicity of that material initially in the blowdown is this graph right here, where we have an Ki of 20. So that it's not just the corrosion inhibitor, there's anything else what is in that blowdown in addition, right, coming out of it. So it's about 20 milligrams per liter versus here, or 20%, I'm sorry. So if that means if my wastewater would contain 20% of the wastewater would be containing, or would be the only the blowdown, then you would expect 50% inhibition of that wastewater, right? So obviously the blowdown doesn't represent 20% of my overall fab effluent, right? But in this case, so that's would be what that number indicates. Whereas if you look at that after the blowdown, you really couldn't find any toxicity, right? So you really didn't find that toxicity. So this is an example where we use that inhibition testing as really as a validation that this new corrosion inhibitor is actually markedly better and reduce the overall toxicity of their fab effluent, right? So that was one example. What we did further, another example is, and we're still working on this, is what happens when you go in the fab. So the fab is this, like what Mohab described, this really complex entity of many, many processes going on at the same time. A lot of those processes are batch processes, and then this waste gets released into a very complex sewer system. Some waste gets separated immediately, probably doesn't enter the sewer system, versus other wastes go into the sewer system. They get blended, and eventually they get released through the fab effluent, right? So what we see there is, so what we wanted to study then is saying, okay, can we identify streams within the fab which are potentially more toxic than others? So not necessarily looking at the total mass balance, right? In terms of, because one waste might be a high volume versus another volume blended together. We just wanted to look at the individual toxicity of these individual streams. And so I just give you one example. And so for a particular manhole, so we had, in this stream, we had 3 different streams going into one manhole. And so what we did then is we tested these different streams for known inhibitors. So known inhibitors are the azoles. We also measure conductivity. And then for some other ones, we used also TMAH, right? So that's what Moa described before. Right, so we measured concentrations. On these concentrations down here, you see all, if they're not indicated otherwise, are micrograms per liter, so very low concentrations. Right, so remember the azole concentration, the inhibitor concentration was 1 for triazole was about 2 milligram per liter, right? So this would be about 50, close to that, right? So for that particular stream, so you would expect 50% inhibition just because of the triazole, right? So we measured those concentrations in micrograms per liter, and then we measured the inhibition of that particular waste stream. And so the inhibition of this waste stream was 17%, meaning that if that waste stream would be 17% of my total wastewater, then I would expect 50% inhibition on nitrification inhibition, right? So that's how you would read that. Then you have a stream of number 2 and number 1. So each of those we characterized. And then we also measured, after blending, we measured the coming out of the manhole, the IC50s of this. So the toxicity coming out of the manhole is really high, 7%, right? So the lower the number, it becomes more toxic. And so now we try to figure out which waste stream really contributed to that toxicity. And if you just look at only the toxicity, you would say, well, it's probably this waste stream right here, right? Because this has similar toxicity values, and maybe that is ultimately influencing the entire stream, right? So there we have the conductivity of a relatively low conductivity. We have TMMH of 68,000, which is 68 milligrams per liter, right? So, so that's not an azole. These are the azoles, but this certainly has the highest toxicity. So what we went then back is said, okay, can we measure the toxicity of TMAH on its own, which we also did at the same culture, and this is the results we got from that. It's like, okay, TMAH at the same culture, there we got an inhibition coefficient about 320. So that means we would only expect 50% inhibition of that waste stream if it's 300 milligrams per liter, which is significantly higher than the 68 milligrams per liter, right? So we did, so in other words, we can't explain the toxicity of that particular stream based only on TMAH. There's something else in that waste stream which probably contributed to that high toxicity, right? And so that goes back to the analytical testing. This is like trying to find a needle in a haystack in that complex sewer system, where we're trying to figure out what are the chemicals potentially contributing to nitrification inhibition, right? It could be metals, it could be some other organic compounds. And so that's when we're asking the John to pretty much tell us, okay, what else is in that soup to ultimately identify specific chemicals which potentially could impact that wastewater. And that's not cheap, but that's the testing we need to do to link ultimately our toxicity results to the observed, essentially understand what we have to do in terms of manage this wastewater. If we know, then we could just say, well, this is a very toxic waste stream. Maybe we don't put that in the sewer system. We just ultimately treat that separately. Right? So that would be the answer from an engineering perspective to say, we're just going to keep that separate and ultimately reduce the toxicity of the overall impact of the fab. Right? So that's kind of the usability of that testing. And so we are continually working with the fab to ultimately identify those particular waste streams so we can source isolate those waste streams from the main wastewater stream. Right. So I pretty much said on the bottom there, it's like we just need to understand, in addition to just looking at individual compounds, we need to also understand what do mixtures of chemicals do to this overall net impact, right? Because it's not additive. I mean, we're adding a whole bunch of chemicals together. It's not necessarily an additive effect in terms of toxic effects. All right, so in summary, I showed you a couple of essays, how we can ultimately use this tool, these batch experiments to identify, maybe make decisions within the fab to make it less impactful for downstream processing, wastewater processing. But obviously, we need to link that tool with analytic methods or sensors to ultimately identify the specific toxic elements. There's more science to be done to ultimately close those. All right, I think that's the last slide. Okay, thank you. Yeah.
Question. This is all on biomass and sludge that is already acclimated to this wastewater.
That's correct. Yes, that's correct. Yeah, no, that's absolutely correct. Yeah. Mm-hmm. Yeah.
Another clarifying question. The date of the foundry that you're examining, it was built when?
It was built many years ago and then modified.
Timeline there and how the technology is.
Right. So in our case, I mean, I think that they're essentially, we've done the testing over the last few years. So they're building chips which go into your phone right now. So I think they're using the state of the technology in terms of manufacturing, right?
Their waste systems go back.
Might be different. Yes, I agree. Might be amended. Yeah. Yeah.
Another clarifying thing. The waste stream number 3, which you identified as toxic, you already know it has no azoles in it.
Yes. Yeah. So we analyzed azoles for all of those. Yeah, there was an azoles. Yeah.
All right, I'm up third and last before we get into the question periods. First of all, I want to thank the College of Environmental Science and Forestry for having me here. Both Stefan and Noah were great presentations for a preamble into what I'm going to talk about. So since I am at the ESF, anybody know what xylem biologically means? I would hope so.
Oh, plants.
So basically, it's the vascular tissue that conducts, the water and nutrients up into a plant that basically form the plant, the woody substance of that plant. Where's my folder here? And I know there's a lot smarter people in this room in their respective fields than I am. And the crazy thing is when I looked at Moha's timeline of fabs, where I sat on that timeline kind of scared me. That was back in 1985 when I started doing this. So it was an eye opener for me. So xylem is also very much a municipal and industrial global water treatment company. We move water, we treat water, we sense for water, and we also, are a very diverse company. And I wanted to talk a little bit about this because we got lots of students in the room, and from a recruitment perspective, always looking for new graduates to join the organization. We're in, we have over 250 service locations. We're in 150 different countries. Again, very diverse representation in the organization, encouraged. And I think these are the revenues for 2023. We're well into, about an 8.5, $8.6 billion revenue organization globally. And like microelectronics is one of those areas that we play in from a vertical perspective, and that also includes PV, data centers, and battery manufacturing. So we're in a lot of areas just from that, but also every other industrial market that you can think of, including mining as well. So that's the only company pitch I'll have. Treating, you saw the complexity of Moha's waste stream, okay? What we as an organization need to do is we need to look at those streams and we need to look at those challenges, and we need to be able to take a wastewater that is in some cases constantly changing and trying to predict where it's going to be on the, the next chip generation and whatnot. So what we have is we have a facility in Pittsburgh that is a full treatability lab and sustainability hub, where we can test anything from anaerobic digestion to physical chemistries to inorganic and organic chemistries in the facility. So not just microelectronics wastewater, but a number of other wastewaters. However, when you look at the complexity in this industry, it is really a challenge. Not only is it a challenge, we don't have time. We have very little time to react to a stream that they are going to change. We normally get 5 quarters to come up with a solution. And the reason for that is just the time to market for this industry is so sensitive from a revenue generating perspective. Sorry, I'm getting old. I have to have notes. So, oh, and in addition, I just wanted to say one thing. In addition to the facility that we have in Pittsburgh, Xylem also has an innovation and accelerator program, which is very unique in the industry. No one else has it, where we actually are looking at universities. We're looking at what's going on in the water treatment sector. We're also looking at emerging technologies that might be beneficial to obviously our customer base or our, our utilities going out there. So, and that is, it's a kind of a little bit separate from the company, but always looking for new technologies to meet demands in the ever-changing waste facilities here. So let me get to the challenge that we had. We had a semiconductor facility that was increasing production and was going to basically be discharging azole compounds to the local authority. The local authority finally said, we are reaching the limit of what we can take from an azole perspective into our facility. So they were obviously able to deal with it, but we're reaching a point where they were either going to have to increase their infrastructure or this semiconductor facility would have to reduce the amount of azoles. There wasn't really first of all, there's no online metrology for azole detection at the moment. We're working on it, but it's not there today. So we utilized both the Pittsburgh facility, our innovation labs, and we did extensive testing around azole destruct, and obviously looked at advanced oxidation processes, mostly trying to utilize UV so that we didn't have to implement too much chemical. However, given the background of these waste streams and what's in them, the UV intensity gets impaired. So we kind of stepped back a little bit and said, let's look at some physical chemistry of what we could do to break down these azoles. So we looked at phentons, and phentons obviously is a phys chem advanced oxidation process using usually an iron sulfate and peroxide to produce enough hydroxyl radicals, which even in the AOP process is what you want to try and drive to break down certain compounds that are not easily broken down. So in our testing, we used sulfuric acid for pH adjust. And then also, actually it was, so I think that was peroxide, not sulfuric acid. And iron chloride were added to basically a test that I'll show on the next thing, on the next slide, sorry. We used, kept a constant temperature of about 60 degrees C in the reaction. You can see the cumulative doses of peroxide that were also used from that perspective. So we're using both the ferric chloride and the peroxide along with temperature and time to work on breaking down those azoles. And you can see in that timeline, a reasonable timeline, anywhere from 120 to 135 minutes, we're able to get 90 plus reduction of all azoles that were in that waste stream, thus being able to reduce what's now going to the outfall of the facility. And what we can do is, and what we're finding is that there's a limit that usually the POTW can take, or that if they've got an end of pipe reclaim with a biological system, there's a point at which they're going to run over that toxicity point. So we're able to adjust that chemical and time, to reduce the amount of chemical we might use and still meet those minimal parameters. So the first test we did on a summary of the results was we actually didn't start taking samples until 50 minutes into the reaction. Simple setup with a beaker, heater, pump, recirculation, dosed, and you can see over the timeline what the concentration reduction was. The chart on the bottom was a little experiment we did on behalf of the customer and some ideas, is rather than use, raw chemical, peroxide and ferric chloride, we looked at some of the other waste streams that were in the facility that already had peroxide and some metals in them that we might be able to use as a catalyst. And you can see that we did get some results, but not as good as results as we would like to have seen in test 3 and 4. And I can say that the benzol triazoles are readily removed in the process very quickly. It's the, pyrazoles and 1,2,4 triazoles that seem to need that longer time in order to break down in the system. The other part of it is the analytical methods were not very clear on actually measuring azoles in these waste streams. So we ended up working with a lab that we work for with our PFAS solutions. And to Chuck's point, he was rather upset when we sent him the first samples and he tore up his mass spec chromatography unit. And this is where I get out of my I'm a mechanical guy, so this is where I kind of get out of my depth a little bit. But he was able to basically, he utilized the chemical derivatization, I can't even say these words, you know what I mean, of these compounds, and he was able to sort of segregate them, and then using triple Q mass spectrometry, can't even say it, I'm Canadian, I can't say these words. And he was able to greatly improve, measuring those and getting the sensitivity. So we were able to confidently look at those numbers and understand them. And with that, again, I said that the benzoyl triazoles were relatively easy to sample. We actually, he did some overspike sampling in order to see what the recovery was. And you can see it was, and we did from a duplicate sample perspective, we were within, 2% to 5% of relatively difference from a difference perspective. And we actually made some dummy samples in our facility to send to the lab to see what the results would be. And they were within 2 to 5% accuracy. So we were also, the client we were working with had their own method for measuring azoles and the azoles that were in the stream. And from an analytical error perspective, we're again within 2 to 5%. So we're confident with the numbers that we're seeing in the process. Just a little bit about the process itself. It's really it's a feed and bleed from that perspective of using temperature, obviously the ferrous chloride and peroxide for the reaction. We're running at about 60 degrees C or 140 degrees Fahrenheit. And it's that with the recirculation, we're able to do a lot of heat recovery. So we're not wasting heat at the end of the day. And the package itself is a full off-site manufactured package, which you guys have no desire to know about and whatnot, and just kind of what the materials are from that perspective. And what we have found in the field is we actually have 2 of these up and operating now, and we are getting better than the predicted. We kind of, as an organization, you got to guarantee a number, so we guaranteed 90%, but we are getting upwards of 97, 98% destruction of the azoles. There's my contact information, and Charles Powley is our PFAS lob solution guy who actually put all the analytics together for us for azole detection, and actually has done a couple of papers on what they've done in this space, if you're looking for that at all. Sure. And then finally, obviously, to Moha's first presentation where he talked about all the wastewater streams that are in a semiconductor fab, azole is not our only stream that we treat for. We are both in the ultra pure water production side of the fence, in addition to any of the other waste streams coming off the facility and water reuse. And I'll leave you with the one on, we talk about resilient communities. We are very active in the community, and I have what's called Watermark. And some of the incredible things we've been able to do. I don't know if anybody familiar with the Hurricane Helene that came through here not through here. I imagine you got remnants of it, but North Carolina, it totally destroyed their drinking water system. And we were able to have them back up and running with a temporary drinking water system in 90 days. Just some of the efforts that we can do as an organization. So I appreciate your time. I'm going to stick around the poster section for questions and whatnot, and I think we have time for questions now, Stephen.
Yeah, so I think at this point, we want to open the floor just for general questions, for any questions you might have to any of us in terms of treating this type of wastewater or some methods or questions you might have or discussions. Yes.
So just overall for a non-wastewater engineer, the studies that you did of the azoles and the treatment, is to design a pre-treatment system so you don't interfere with the municipal treatment process as an overall objective of the work that you designed?
Yeah, so I think the idea was, in this case, was for the manufacturing facility to understand, one, what are the waste constituents which ultimately could impact the wastewater treatment plant where they're sending their waste to, and also to provide them a tool to manage their waste maybe more efficiently, right? So in terms of the corrosion inhibitor tool, they could essentially, substituting one chemical for another, reduce the toxicity, right? So it's a management tool for inside the fab in this regard. But you could also see it for a management tool for a municipality that could go through their sewer system and say, here, these waste streams are more toxic than others, to my wastewater treatment plant. Right? Yeah.
Okay, thank you very much. Why do you think the regulations are not actually advancing the way the semiconductor industry is advancing? Because it seems so slow, the regulations, right? Yeah, why?
Yeah, he's an ex-EPA guy. You can ask him that question.
There is the right way to answer that, and there is the honest way to answer that. Follow the money. It's a very rapidly moving animal. So many different things are changing. To regulate, mean you need to understand enough so that you can have defensible kind of data set. And that's why I was intentional in showing the timeline. Yeah, it was decades, but from a regulation point of view, it's not that fast. It's actually, yeah, when you change a soup of chemical with one ingredient, you need to reevaluate the whole thing from the beginning to make sure that it's following certain procedures. So that's one reason, but there are many other reasons.
And can I add to that a little
Yeah.
bit? Let's not just pick on the semiconductor industry.
Yeah.
You know, here, at least my mother was ecstatic when she could cook on a Teflon pan, you know, many years ago, from that perspective. So there's a lot of industries that are, you know, it's definitely an issue. And I don't do the regulations. I think we're seeing more state regulations on it than I think we are from an EPA perspective. And we, you know, we have ways to treat it, which is good, and we're expanding on some of those ways as well. So.
You have a question?
Yeah, and it's sort of in that realm, but I guess relative to the timeline of just how fast this is all going and the timeline that, you know, you would need just for one of those particulates to try and like destruct them and stuff like that. How, I don't know how to ask this, like how far behind are we before we wind up in a really bad situation where like we really can't handle whatever loads are coming out, if that makes sense?
Do you want to take that? Yeah, for that specific discussion, I guess we're not trying to be alarmist because one of the facts.
Well, it's hard.
No, but one of the facts that there are activities. I mean, like when I showed you the 21-step treatment train, this is not a future-looking or hopeful kind of prediction. This is happening now.
Exactly. That's
So-
what I'm saying.
So that's why I wouldn't see us being in a very dire situation. That the main thing, can we be in a better situation? I guess this is the answer, can be easily said yes. But where can we focus our attention? And that's why I put, like you see, like air, water, solids, the interconnectivity among them, the residuals. There are some overshadowed questions, like there are some focus on certain areas. And that's why I'm trying to say, just like, need to zoom out, we see where it works well, where things can be done in a feasible and meaningful way, where things that would be just, yeah, not really productive. And that industry can easily say, like, there is no regulation, I cannot do anything, or I don't have to do anything. But I think there are activities from a proactive move that kind of getting better.
I guess let me add to that. I think the other thought I had is like that we are using, I mean, any industrial facility at this point are regulated very highly for a lot of aspects. And so the technology to treat the waste is there in most of the cases, right? And I think the question we have is like, how are we prepared for new chemicals, for new toxins, or to be more efficient or economical to ultimately manage these complexities, right? So as you get new waste coming in, do we just add more end of pipe regulations to make, essentially say it has to be cleaner and cleaner and cleaner, so we add more unit operations to his waste stream process? Or do we incentivize the company to say, you look within your plant to source separate, to manage your waste better, that you don't need that incredible wastewater treatment plant at the end of the pipe,
Mhm.
right? So I think we need to figure out a way to, yeah, to do both, right? To protect obviously our environment to best we can, but also not to make everything. We don't necessarily need to treat our wastewater to ultra pure clean drinking water, right?
Right.
Which the technology will be there, right?
So I guess for all three panelists, including the Canadian, my one is, the demo has happened and there's design build for municipal upgrades as well as industrial wastewater treatment plant. That's what you presented, looking at fair risk, what is known, what chemicals, we don't even know if there's any assays or anything to look at right now. Do you think that, oh, and the biggest part is that the effluent will go into Lake Ontario, miles from the drinking water that comes to Syracuse, but eventually dilute out to Ontario? Do you think Micron should be built here with the current technology?
Ooh.
Ouch.
Yes.
That's a good question.
Elephant in the room last session.
Canadian? I'll take, yeah, I'll take that. Well, I live in Portland, Oregon. now, but That's okay. My wife always teases me on how I pronounce words, but, look, I have been in this industry a long time. And I would say that this industry takes one of the highest precautions on where they go and the environment. So I'd be pro, yes, for a build.
Are you waiting for me to?
Yeah.
Oh,
You said all three.
I guess based on the available information and what can be done. I guess, yes, there is some engineering solutions that can be helpful. It's again, I think one of my the last slides was like, what can be done before you have an engineering like design freeze? That's why I'm putting emphasis on that, because if someone is in that phase of trying to build versus stuff that had been already, like the train had left the station already, then that can be done in a good way. So my information about what is the level of awareness about liability and what should be done, what shouldn't be done, I think it is there, and that just gives me, yeah, should be done because from an economic point of view and can be done in the right way.
Environmentally too, right?
Yeah.
Okay.
Yep, I guess my comment would be I guess the question would be the transparency is a critical aspect, right? Do you need to understand, as long as that all parties are transparent in the way of what chemicals are there, what information they're using to ultimately make their decisions, then it can be validated by independent people to look at the appropriate technologies. Because I think the technology for most of I would imagine for all of those chemicals is there, right? So the technology is there. It's the question of what technologies are we using for what removal of those chemicals. And so I think, so that goes back to the transparency question. As long as that is shared and validated by all stakeholders, I think that would make sense. Right?
Can I follow up on that?
Sure.
So what we were faced with is a complete lack of transparency with respect to the Micron project. And that's the chemicals. There's actually a lawsuit about that. The EIS, which was 20,000 pages, failed to identify the chemical. And so there's a big gap there in terms of information that's being disseminated to the public. There's also the technology, the treatment technologies being used at Micron in the plant is a black box. We don't know what that is. And as been pointed out, the final requirement for treatment is dictated by regulation more than anything else. And the regulations, as you pointed out, are way behind. So we have a situation where the state is saying, okay, we want you to look at two compounds, PFOA and PFOS, which are legacy compounds. They don't use this. And what about the other 300 compounds of PFAS? We don't know. So there's a lack of, there's a big gap there in terms of transparency.
So that creates worry with the
Yeah.
public.
Exactly.
Not that you guys are
No,
responsible.
no. But what I can comment on that, I was on a call with someone, cannot identify the source here, obviously. But do they know? Yes. Did they do that on their own without any push? Actually, yes. They have a list of PFAS compounds that was developed in 2023. And I was told that they are preparing to release another one that includes ultra short chain, things that are not regulated, they're not really have any regulation push to do it. But what I'm liking from the discussion here, because this is needed, I mean, like the pushback, the continuous kind of request for information is the balance that will help. Yeah, EPA on a federal level is lagging behind. I don't think there will be a recovery anytime soon. But from a state, I guess, source control, I heard from a commissioner in a conference when she was recently appointed that source control for certain industrial will be part of it. Not saying that they are going after the semiconductors, but that just flags for me that would be like controlling the pollution at the source is, if it is priority for the state, that's a good sign. But the continuous, just like what question to ask and who to ask, is a black box is also can be justified, just like no company in that very competitive kind of landscape will be just willing to give away everything that they know about what designing or developing internally. So maybe tweaking the questions and going in different channels in the one.
I'm going to say one thing to that question. And yeah, I understand the concerns. I can't speak to any one customer, but I can speak to the industry. I sit on the IRDS committee for yield, but which is the International Roadmap for Devices and Semiconductors. Again, I've been in this industry a long time. And I would say from a sustainability and environmental impact perspective, it's a leading edge technology. It's leading edge industry of like the semiconductor industry was looking at sustainability before sustainability was really a buzzword at the end of the day. So that's why I am pro for seeing these facilities go in. They're needed. We all want AI. We all want our cell phones. Okay. Anybody raised their hand who does not have them?
But here's the thing: there are certain industries that I don't. Maybe the trust isn't the right word, but there can be a lot of red flags in the discussion with them because I can see a lack of understanding of the problem. Not endorsing anyone, but when I showed the two treatment trains, it's again just like they have the brains that understand treatment. If we're worried about water treatment, I wouldn't worry like to talk to them. They will have someone who knows how to treat the water. There are other industries that would claim to know something about it, but you talk to them, obviously they don't know anything. And that's a much bigger risk, because if they claim that they are trying to solve it, but they don't know that the problem is there and how to actually deal with it, that's a much worse scenario. But if someone is, again, treating the water to the ultra pure level, they have the know-how, and that just gives a level of comfort.
Well, we still have challenges in that. But that's okay.
Yes, but it's again from expertise point of view.
Yeah.
So, question, how would you incentivize Micron or other semiconductor manufacturers to use the best, new technology to eliminate food waste? How would you incentivize them to take that on themselves without regulation?
Without regulation?
Regulation, political system
Yeah.
is not here.
Right.
So seems to be that elimination at the source was the most effective way of eliminating waste. So from your experience, how would you incentivize them to do on themselves industrial level of technologies? What's the
Well, I guess the obvious one would be cost, right? So if you were to, but that would go back to permits. It's like if the company would be faced to treat their waste at a very costly rate because they didn't substitute chemicals, they would be incentivized to come up with substitutions because they would save money, right? And so, but that would be meaning essentially that you would have to impose high treatment costs or standards to them, so they actually incur those treatment costs for the current chemicals they use it. Right? So that's regulation again, right? So, but that's really the main incentive, right?
That's why we're new.
Yeah, the main
Because
incentive.
there are no regulations.
Right.
At this point.
Well, I mean, I know, I mean, the fab we work with, they have discharge permits, right? And the discharge permits are set by the DEC, right? And the discharge permits are essentially assessed based on, they need to set them based on their internal assessment on toxicity or net downstream impact of that wastewater system where they're discharging into. And so the pre-treatment, yeah, right. And so they're setting standards, pretty strict standards to the fab because of their perception, what they would ultimately, that wastewater would impact the downstream wastewater treatment plant, for example, right? And so they have a standard. So they do set standards, right? They do set, the DEC sets very strict standards for the particular waste streams. Yes. And that's a permitting process, through their permitting process. Right. And so they would set standards for any kind of waste, any discharge, right?
It's the municipality that sets that.
No, DEC does that.
Not the country.
For an industrial user permit, it's discharge.
Yeah. Right.
Yeah, that's the DOT.
Yeah.
Yeah.
You know how specific the DEC standards actually are, because there are so many, like hundreds and hundreds of different types of PFAS and PFAS. Do they have to state every single PFAS and PFAS they know in order to like have regulations, because they're being, you know, how do you check for every single one, because you don't have a standard unit test? How do we know that they're actually connected?
What I know of, I mean, I think DC is looking at, what is it, 40 some compounds, right? At this point. Yeah.
633, yeah.
Yeah.
One of the
It's
issues
something
is
like
the
that.
fluoride in the background.
Right.
So you can attempt to get total organofluorine, but one of the biggest issues is that you are trying to convert everything into inorganic fluoride and then quantify that. But if you have milligram per liter of fluoride in the background, just obscure the whole data set. They are, and that's why I think I highlighted that NMR attempt, because that's actually funded. They funded a study at University of Toronto to do that. They have a white paper to show that standard methods, even, yeah, AOF is standard, EOF, like extractable organofluorine is not, but both of them you will get non-detect, and that's because of the high detection limit. But NMR is being now use because it has better sensitivity and selectivity for different PFAS. So it's work in progress, and I think I highlighted that analytical challenge multiple times because it's, again, we can be dreamy and demand everything that it's best case scenario, but I guess once we have that reality check of just like what can we do, what can we manage, and how can we get the data to back it up, this is where things will start to get more complicated.
Just to follow up, just thinking through the toxicity of the chemicals, where does the Department of Health come in terms of permitting, potential, industry that can cause human harm because of the toxicity when they're not ability to measure these chemicals? Anybody?
I can't answer that question.
It doesn't go that route unless it is food related or it's just like direct human consumption. That's different route because industrial, they'll go to EPA, maybe TSCA, some other chemicals kind of certification and pathways. But Department of Health, I don't see how you can directly correlate that with that.
Oh, because water goes, gets consumed by humans and other animals and also ends up on agricultural land and redistributes all those chemicals on the land.
Yes, and this is where I guess the incentives question comes. This is where the liability cost is actually a very strong incentive, and that's why sometimes they would just take that proactive move. Just you have the permit level is this, we'll try to make it better because if class action lawsuit comes in a couple of years and they are kind of liable, no one can go and hide from that. I mean, 3M and DuPont are very clear examples. But I don't see how the Department of Health gets into industrial chemical process directly.
Thank you, each of you, for your presentation. A lot of the presentations focused on post-processing mitigation. And I'm curious about collaboration and engagement from an environmental protection point of view with the design process in the manufacturing process. If any one of you can talk about that, either through your personal or your organizational experience, to what extent have you been consulted or do you anticipate being consulted in terms of the design of these processes that you're dealing with after the fact in many of these examples?
As we speak, alternative assessment and design of alternative chemicals processes, they are doing that. But until that happen, I guess, even from the treatment part, I guess Ellen was mentioning like the 5 quarters and how aggressive that would, and that's compared to how sensitive and actually very precise the 1,500 steps and hundreds of chemicals. Any change is just like way larger magnitude of when you talk about impact of changing that. So alternative assessment is happening, but it takes time.
Looking at the design of processes, I mean, ideally, you would have no toxic materials to mitigate, and there would be ways of designing the process to minimize those materials.
Yeah, or manage the toxicity, right?
Yeah.
So if you're producing some chemicals which you need to produce for your manufacturing process, which are toxic, you need to isolate them, right? And then treat them separately from the rest of the waste. And so I think, well, from my perspective, I got consulted with this potential nitrification inhibition work, right? So already from some consulting engineers looking at what the potential is and how far we can quantify those. And I think maybe we are too early on in our phase, in our studies, to ultimately identify specific, I mean, there's some certain chemicals, but not others which you can identify. So we can't just, a consulting company doesn't want to rely on just that knowledge, right?
Thank you.
One comment, it's just not semiconductors or fab related, parallel line of my work when I was back at EPA is actually for alternative assessment for PFAS replacements. It was from a fluorine-free foam like AFFF and firefighting foam containing PFAS, DOD, spacing out, bringing more chemicals. So the simple question, are we getting something same, better, or worse? And that's published already. Acute toxicity, I send it to labs across the nation. They don't know each other. They come back to me. They say like, this is the most toxic thing I ever tested in my lab. That's the new chemical. Is this a conclusion about like, it is the worst thing ever happened? No, but there are more testing needs to be done. But comes to the timeline and how aggressive that transition needs to be. Like Congress gave them like 5 years to phase out all AFFF, replace it with fluorine-free foam. Couple of years got extension, etc. But still, you're talking about less than a decade. Are we facing like a regrettable substitution scenario? That's just for time to acknowledge that. But the key thing, and again, that's already published, that the tools that we have now are not actually ready to test toxicity for these chemicals. Aerobic, anaerobic kind of testing. Aerobic one, you need to use aeration. What happens when you aerate a foam? It foams. Yeah, so the standard method, if you follow it line by line, it will fail. So we needed to make tweaks and changes. But once you change it standard method, what is standard about it after all? So that you see like there are a lot of things that moves at the same time. So it's not picking up on certain industry or application, but the alternative assessment and alternative analysis also needs to be celebrated, but with a lot of caution and extra question that needs to be followed up. But I hope that was helpful, but it's just different, but it just speaks to how complex these transitions would be. Like you can get something, but did you really get a better scenario? That's TBD.